Greetings from Marathnesh's College of Engineering. We are Team Srishti, here to present our rover, Prana. Our rover's development is structured into multiple specialized subdivisions, each responsible for a crucial aspect of the rover. From mechanical design all the way through electronics, embedded systems, software, and autonomy. Every subdivision contributes uniquely to transforming ideas into functional systems. This division of responsibility enables us to maintain technical depth in each domain while ensuring strong interdisciplinary collaboration across the team. The organizational structure illustrated here represents a hierarchical and operational framework, highlighting how responsibilities are distributed and coordinated within the team.
For Team Srishti, ERC 2026 is more than a competition. It is a culmination of years of effort, sacrifice, and belief in what student innovation can achieve. Behind every component of our rover are countless late nights, failed prototypes, technical setbacks, and hours spent learning far beyond the classroom. It represents the times we chose engineering over comfort. Missed outings, sleepless nights, postponed celebrations, and risks willingly taken to build something meaningful. We want to participate in ERC 2026 to prove to our professors, peers, institution, and most importantly, ourselves, that every hour, sacrifice, and resource invested in this journey mattered.
The first prototype of Prana featured a 6-wheel bogie with a rocker bogie suspension system. Second iteration of Prana created the current base of our rover, the modular 4-wheel bogie that integrates independent swerve steering into an inbuilt rocker differential kinematic suspension system. The rover's rigid chassis is manufactured from aluminum 6061 pipes, forming secure structural frame that supports the sheet metal center body. The latest version of the rover features the kinematic differential suspension system, where the axis of the rocker arm and the steering arm intersect at a point that was previously an opposite, causing a load on the steering arm and resulting in the torsional effect on the rocker arm about the axis through the rocker arm. Aligning the axes and making them intersect eliminates this risk, enables structural integrity, and helps to eliminate wide movements of the wheel through the track axis. The tires feature a flexible TPU outer layer with honeycomb infill and a 3D printed rim, optimizing the balance between flexibility and rigidity, allowing for controlled deformation, better contact, and shock absorption. The initial design included a 3D printed PLA gear system, which later evolved to be inefficient, leading to the change into quartz planetary gearboxes. Rover's BMS is controlled by a custom-made PCB, which is manufactured in our CNC facility at our college. We use high-efficiency buck and booster systems to regulate the varying voltages across the drivetrain and steering system, and lower logic voltages for sensors and control electronics. The Bowman Tower light indicates the visual response of the rover's operational states. The electrical power is drawn from the multiple 6S LiPo systems, which is made into a modular architecture that allows individual power packs to be independently isolated, recharged, and replaced. The onboard kill switch swiftly addresses the emergency situations. The schematic includes the circuit design of the rover, integrated payloads, all wired with various silicon wires for high temperature traversal. The rover processes real-time orientation from IMU along with magnetic encoders using sensor fusion methods such as Kalman filters, complementary filters, etc., which ensures tight synchronization across all drive and steer actuators. The visual and positional data integrated from the Z2i and auxiliary cameras provide much more accuracy towards the localization of the rover. The onboard processing is done by a TNC 4.1, which acts as a high-speed electric brain. The system is powered by a high-performance AMD Ryzen 5 900 and RTS 3050, running Ubuntu and ROS 2 Humble.
For locomotion, our rocker suspension system incorporates a fully independent servo steering architecture.
To ensure responsive and seamless handling, the drive system relies on closed-loop feedback governed by rover-specific kinematic models. We implement precise PID control loops utilizing position control for the independent steering modules and velocity control for the drive motors. Because of this integration, the rover natively supports multiple complex driving modes, including traditional Ackermann steering, zero-radius in-place rotation, and omnidirectional steering.
Powered by NAV2, the autonomy stack incorporates OPSLAM3 visual odometry, IMU, and wheel odometry for local localization.
For global positioning, an EKF incorporates absolute pose estimates derived from an OpenCV Aruco pipeline and YOLO V11 detected natural landmarks. Our tap map generates post-mission 3D environments while feeding a projected 2D map to NAV2, which we augment with slow-power traversability layers to safely navigate the Mars Yard's uneven terrain. Finally, a core control program orchestrates overall mission planning.
The communication between the rover and base station is done through Rocket 5 AC lag, acting as the primary RF link utilizing the 5 GHz spectrum. The rover uses an omnidirectional antenna ensuring 360-degree coverage, and a high-gain sector antenna with a 120-degree beam width is kept at the base station. Video, telemetry, control commands and data are sent to the base station and are visualized in a GUI.
Sea Cooper is designed to be a modular drone with 10-degree downward tilted arms for improved thrust and flight performance. The drone design was validated and substantiated by static, structural and vibrational FEA, along with CFD analysis of the propellers. The landing gears features TPU pads for shock absorption during landing, propeller guard, enhance safety and protect the components, while the central body houses the electronics and payload in a compact, optimized enclosure. Sea Cooper features high-thrust, low-ampere motor powered by 5000 mAh battery with a powertrain optimized for sustained low-altitude flight. Dual M10 GPS ensure reliable localization and surveillance. For precise stability even under low GPS condition, we use Holybro H-Flow optical flow sensor. Probe detection is performed using thermal camera powered by Jetson A203. Long-range communication is ensured via CE HM30 system, all coordinated by the Pixhawk 6X flight controller. Sea Cooper navigates a 10x10x4 meter gauge using Q-ground control defined paths, while ROS2 handle real-time processing. The YOLO 11 algorithm detects probes, align the drone overhead, and log GPS position. And once all the probes are marked, it autonomously lands on the Aruko 102 target with precision.
The rover is equipped with a 5 DOF manipulator consisting of 6 revolute joints along with the custom elevator. It incorporates 3 in-house cycloidal gearbox with a 19:1 reduction ratio, where the major parts are made of mild steel and remaining parts are 3D printed in PLA. The links are carbon fiber ensuring durability. It is actuated using DC brush motors with incremental quadrature encoders, controlled by TNC 4.1 microcontroller. The system supports both joint and Cartesian control using ROS2 with onboard motion planning and Jacobian-based velocity control. A RealSense D435i camera mounted on the end effector enables perception with YOLO V8 used for real-time object detection and depth-based localization.
For the maintenance tasks, our custom in-house manufactured 2-finger adaptive gripper combines aluminum and 3D printed parts into a versatile end effector with a 120 mm stroke. Designed for high-mix pick-and-place operations, the fingers mechanically adapt to payloads, curling inward upon resistance to fully encompass objects or achieve a secure pinch. This built-in adaptability eliminates the need for complex control code, allowing the gripper to be driven by simple open or close commands.
For surface sampling operations, the manipulator deploys a dedicated actuated scoop mechanism designed to efficiently penetrate and excavate loose regolith.
Automated auger drill system is designed to collect deep soil samples from about 35 cm below the ground. 2 top-mounted motors lower the system smoothly along metal guide roads for accurate vertical movement. Once the required depth is reached, 2 belt-driven motors rotate the auger drill to penetrate the soil. The spiral auger then lifts the soil to a transparent cylindrical container, allowing easy observation of the collected sample and soil layers before dumping.